Hello friends, in the previous sections we have introduced node analysis and mesh analysis, and we did some problems in that so that the idea of application of the nodal analysis and mesh analysis to problems will be very much clear to you. Now with that we can conclude the nodal and mesh analysis because as we go through the course we will be encountering circuits in which you will have to select which particular method to use. Either use node or use mesh based upon your preference. Therefore, the concept of node analysis and mesh analysis will carry throughout the circuit analysis. So it is not actually getting stopped there. It will continue. As such, the last few lectures were to introduce you to the idea of node and mesh analysis. In this particular session, we can call it to be a new topic as such. We will be introducing useful circuit analysis from what you can see, which is already in the screen now. Now, what we will be learning here is not a replacement for nodal or mesh analysis, because for any circuit to solve systematically, you have to use nodal and mesh analysis. But use of these techniques will make the circuit easier, or it will convert the circuit in such a way that it will be familiar to your liking. Alright, so if you are comfortable with node analysis, you can use a particular technique and the circuit will become more node friendly circuit, or it will become a mesh friendly circuit. Alright, so it will become a personal preference. That is why I tell you there is no hard and fast rule in circuit analysis of which particular method to apply, because in most of the questions you can use either node analysis or mesh analysis, or you can convert them into a form that you like. But of course there are some problems where mesh analysis is easier and node analysis is easier. Well, that comes out of practice. So you practice continuously, and just by looking the problem itself you will be able to get the idea. Now what we will be seeing here in this particular sessions, in this series of lectures, we will be seeing these particular topics. We will be starting with superposition theorem, alright, a very important theorem, and then we will be doing source transformations, Thevenin theorem, Norton's theorem, maximum power transfer theorem, and delta to star and star to delta conversions. So basically all these techniques are useful in circuit analysis, but they do not replace mesh or node analysis. Ultimately you will have to use one of the particular technique, or you will have to use Ohm's law or KCL, KVL, anything you will have to use to get the final result. So as the name suggests, the first one is going to be the superposition theorem. Alright, so let us start with superposition theorem. Let us take the new page here, fresh page. Yeah, so let us start with the superposition theorem. Superposition theorem. Alright, now basically superposition is the consequence of linearity, and we are dealing with linear circuit analysis. So let us just do a little bit of background check here. So what are linear elements? Alright, I have already defined what is a linear element. Alright, what is a linear element? Linear element is an element which has a linear voltage and current relation. Alright, so what does that mean? It means that if I multiply the I by K, the voltage also gets multiplied by K. So if I turns to K into I, that means the voltage turns into K into V. So that is the concept of linearity or linear elements. Then we came to linear dependent sources. Alright, linear dependent sources here. Alright, so what is a linear dependent source? I have already told you linear dependent sources are sources which are depending on the voltage or current in some part of the circuit. There also the definition of linear dependent sources is that the dependence is only to the first power of the voltage or current. Dependence is only to the first power of the voltage or current. That means if you have a current source here, it is 4 into Vx, so this is the first power. Alright, if you have a dependent voltage source and it is some 4 into Iy, this is also the first power, then only you call it a linear dependent source. Now what is a linear circuit then? The linear circuit we have been going throughout the course. It is a circuit which contains only linear elements, alright, like resistors, inductors, capacitors. It contains linear elements I'll just write it here. It contains only linear elements, linear dependent sources, and linear independent sources. All right. So this is the definition of a. I did not write linear actually, because dependent sources itself is a constant value, and dependent and independent sources. All right. So this is the definition of a linear circuit. Now, what is superposition theorem? The superposition theorem is the direct consequence of this linearity. Direct consequence of this linearity. Now, what does that statement mean? This statement can be easily explained only by using a simple numerical. All right. Let us take a simple problem here now. All right, now this is the simple numerical which I have taken, which is very familiar to all of you, because you have already gone through all these problems in nodal analysis. So usually what do we put? We put something like this V1 here, and we put something like this V2 here. Now here the independent sources are IA and IB. All right. Now because IA and IB are the independent sources, whatever effect is there in the circuit, it is caused by IA or IB and the effect of these two particular independent sources. All right. So IA and IB are called the forcing functions. All right. They are called the forcing functions because they force a particular response. All right. And the consequence here is the node voltages V1 and V2. So V1 and V2 are the consequences of this particular forcing function, and therefore they are called response to the forcing function. All right. So let us now write the node equation here. So what we will be getting, we have already applied it at node 1. If we apply, so you get minus IA, I think I'll use black, yeah, minus IA plus V1 divided by 2 plus V1 minus V2 divided by 2 equal to 0. All right. So what do you get here? We get 0.7 V1 minus 0.2 V2 equal to IA. All right, this is what we get here. So let this be equation. No, let us not name this equation because we will be changing it. Now let us write the node equation at the point node number 2. So you get minus IA plus V2 divided by 1 plus V2 minus V1 divided by 5 equal to 0. I wrote a KCL equation there. So I get here minus 0.2 V1 plus 1.2 V2 is equal to IB. All right, I get these two equations here. So let us keep that here. Now let us conduct an experiment. All right, we are going to conduct an experiment. All right, what we are going to do is that we are going to replace this current IA by IAX and this IB by IBX. So IA becomes some other current value IAX and IB becomes some other current IBX. So if you write this equation, the only thing which is going to change here is V1 and V2. So it will become, say, 0.7 V1x minus 0.2 V2x equal to IAX. All right. I've just written this in terms of the new quantities. So the second equation is minus 0.2 V1x. All right. Plus 1.2 V2x will be equal to IBX. All right. So this is the first experiment. So experiment number 1. Let us take experiment number 2 here. All right. In which I am going to convert IA into IAY. I am replacing the current IA with IAY and IB with IBY. All right. So by the same argument, this first equation will become 0.7 V1y minus 0.2 V2y equal to IAY. All right. Minus 0.2 V1y plus 1.2 V2y equal to IBY. You might be getting a little bored, but please bear with me because the consequence is going to be interesting and very useful. All right. Now let me just take this equation to be A, this B, and this is C, and this is D. Let me just add two terms here. All right. I am going to add A plus C. So adding A and C, I will get 0.7, all right, into V1x plus V1y. All right. I'm just adding this term and this term here. All right. Minus of 0.2 into V2x plus V2y, alright, is equal to IAX plus IAY. I have just taken the two forcing functions and I have just added them together. And the next, as you have guessed, we are going to add B and D. So B plus D. So first I took these two and then I took these two. So what will I get? I will get minus 0.2 into V1x plus V1y plus 1.2 into V2x plus V2y. And this is equal to IBX plus IBY. Okay. Let us just copy this equation and let us take to the next page. Now I have copied the terms to the next page here now. And what I have done extra is that I have just written these two equations out of the first result before and the second result before taking the experiment. I've just written these two equations side by side now. I've just written these two equations side by side. Now let us look at these equations. You can see, for example, if IA was equal to IAX plus IAY, that means you are selecting the IA term for the first experiment and IAY for the second experiment such that the sum of these two is the current in the first place. Alright. Similarly, if you had selected IB equal to IBX plus IBY, alright. Now what do you get the let me call this as the total response, total forcing function. Alright, this is total forcing function because IA is the forcing function, right? Okay. Now, and this was the total response. So V1 and V2 are the total response. So this is the total response. Okay. So you can clearly see that this V1 will be equal to V1x plus V1y. Now what is this? The response of the first experiment. Response of the first experiment. And this is the response of the second experiment. Alright. This is the response of the second experiment. Similarly, this is the response of the first experiment and this is the response of the second experiment. So what it basically means is that when your total forcing functions is divided into two particular experiments and you get individual responses, the total response is nothing but equal to the sum of the individual responses. And this is basically what is superposition theorem. See, to make it more, having more clarity, you first performed the experiment X. Alright. So with that you got V1X and V2X. Alright. Then you performed the experiment Y. Then you get V1Y and V2Y. V1 and V2 are two different terms. So it means that, so this is the individual responses. That means the total response, alright, due to the experiment X and the experiment Y will be the individual responses, which is V1X plus V1Y and V2X plus V2Y. And this is the essence of superposition theorem. Alright. So basically in superposition theorem, what we do is that you select one forcing function. Alright, you select one forcing function and make the other forcing function 0. Other forcing function is set to 0 and calculate the response. So for example, you are having a voltage source, independent voltage source and an independent current source in the same circuit, and you are asked to find the current through a particular resistor. So what do? You first select the voltage source and you kill the current source and you find the current value. Next you select the current source, you kill the voltage source, then again find the current, and the sum of these two will yield the total current which is required. So how do you kill a voltage source? So if you have a voltage source, independent voltage source V, how do you kill this? You have to make the voltage equal to 0, right? you make the voltage V equal to 0. So how do you do that? It is basically a short circuit. You just short the voltage source, you have killed the voltage source. So in superposition theorem, if you have to kill the voltage source, you replace the voltage source with a short circuit. Now similarly, if you have a current source, all right, you are having a current source here with some current I, and if you want to kill the current source, what do? You make the current source value to be equal to 0. How do you do that? You replace the current source with a open circuit. Therefore, if you have to, while using superposition theorem, if you have to replace the current source, you have to kill the current source, you replace the current source by a open circuit. All right. With this, let us see the formal definition of the superposition theorem. All right. So this is the statement I have written about the superposition theorem, and some points are very important and you should never forget. So basically the statement is that in any linear circuit element, linear resistive network, the voltage across or current through any resistor or source may be calculated by adding algebraically all the individual voltages or currents caused by the separate independent sources acting alone. This statement is important. All right. This particular line here, the separate independent sources acting alone with all other independent sources set to 0. Now, what does that mean? If you have a dependent source in the particular circuit, you don't replace that dependent source with anything. That will be there throughout the analysis. You only replace the independent sources. All right. So, for example, you are having n number of independent sources. All right. So that means you will have to conduct n number of experiments, which will give you n responses, and the total response equal to the summation of all these n responses. The important thing in superposition theorem is that you have to take care of the passive sign convention, and you have to be very good with that. Otherwise, you are going to make a lot of mistakes. So with that, let us proceed with a simple problem here, and in the next lecture we will be doing a little bit of problems which have independent sources also. But just to give you a feeling of this application of superposition theorem, let us take a simple problem. All right. Okay friends, this is the simple problem which I have taken from the book Hayter and Kemmerly. Now this simple problem you can do easily by a node analysis technique, but how do you use superposition theorem? All right. Now, in superposition theorem, like I have told you, you have to select one source at a time and you have to find the response. All right. So clearly you are having two independent sources here. All right. That means you will get two responses for this particular Ix. You have to find the value of Ix. All right. So that means according to superposition theorem, the total response Ix will be the response Ix due to the 3 volt source alone. All right. I'll write alone also here. In the future, I won't be writing this. And next is the plus Ix due to the 2 ampere source acting alone. All right. So let us take first the 3 volt source. Okay. So let us redraw the circuit quickly. So you are going to select the 3 volt source. Okay. Yeah. And what do you do to the other source? You kill the other source. That means you replace the 2 amperes with an open circuit. All right. This is 6 ohms. This is 9 ohms. And this particular current in this direction, it will be the Ix due to the 3 volt source alone. So what will be that value? You have done so many problems. This is very easy. So it will be 3 divided by 6 plus 9. 3 divided by 6 plus 9. So you get 3 divided by 15. All right, amperes. Now let's take the second case, second experiment with only the 2 amperes. All right. So what do? You have to replace the 3 amp voltage source with a short circuit, right? So you replace the voltage source with a short circuit and you redraw the circuit. So this is 2 amperes, this is 9 ohms and this is 6 ohms, and you get this particular current to be Ix due to the 2 ampere source alone. All right. Now in future, as you do problems, you should not draw these circuits differently. You have to put everything in your mind and you have to calculate, because drawing all these things, especially in competitive exams, it will kill a lot of time. Because in some problems, superposition theorem really helps you a lot. All right, so let us find the value of Ix 2A. This is a simple application of the current division. So it is 2 into the resistance of the other branch, 6 divided by total resistance. So it will be 12 by 15. So these are the two individual responses. Okay, so the total current Ix will be Ix of 2A plus Ix of 3 volts. So it will be 12 divided by 15 plus 3 divided by 15 equal to 15 divided by 15, and it is equal to 1 ampere. So it's a very simple problem that we have taken, but I hope you have understood the application of the superposition theorem. I'll see you in the next lecture where we'll do a couple of problems a little bit complicated so that you get the idea more firmly. I hope you have enjoyed this lecture. Please like, share and subscribe the videos if you like them, and I'll see you in the next lecture. Thank you.